There, this is Mrs. D, and I want to go through some of the practice problems from the stoichiometry worksheet that I assigned for you. That way you can, look back to see if you're correct or if you're struggling at all. This might help you with some of the actual problems that you're doing. So we're going to look at the first one. Number one is broken down into 5 different parts, and it's basically the point is to help you think through the problem. So I want you to look at this, the combustion of a sample of butane. So butane is a C4H10 right here. We're combusting it with oxygen, and our products are going to be CO2 and water, just like any combustion reaction that we've been working with. And what we find is we actually produce, and the information tells us, 2.46 grams of water. And so that is our have. That's our piece of information that we know. And so first, our question is to simply ask how many moles of water are formed. So we're going to simply go from 2.46 grams of water to moles of water. So that is something we've done lots and lots of times before. And so we're going to use the molar mass of water, which is 18 grams of water for every 1 mole of water. And we'll just calculate that. Let me calculate that really quick. So we're going to take 2.46 and essentially times 1 divided by 18. I'm just going to divide it by 18, and I'm going to get 0.14 moles of water. So we're working with this moles of water just to make life easier right now. So now I want to know how many moles of butane were burned. Well, I know the moles of water, but I need to know the moles of butane. The beauty is about stoichiometry is that you can use a balanced equation to find the proportion. So what I'm going to do is take that information I have from above, which is 0.14 moles of water, and I'm going to do what we call a mole ratio from using our balanced chemical equation to determine the number of moles of butane burned. So I come up here to my balanced equation and I have 10 as my coefficient for water. So that means I have 10 for every 10 moles of water that was produced. I used 2 moles of butane because that came from my coefficient for butane. I used 2 moles of butane. So I'm going to go ahead and calculate that because I can cancel out my moles of water and I get moles of butane. So I have 0.14, and I'm going to multiply that by 2 and divide it by 10. So I'm going to get 0.028, and that's moles of butane. Now, I take this piece of information and I'm going to use this on the next page. So what I'm saying right now and what my problem's reading is that when I have 0.028 moles of butane, I am able to produce 0.14 moles of water. Let's take a look at the next problem. So now my question is, how many grams of butane burned? Well, I just found from the problem before how many moles of butane, so I'm simply going to take the moles of butane and convert it to grams of butane. So I have 0.028 moles of butane, 0.028 moles of butane, and I'm going to simply convert that to grams. And so I take my molar mass here is 58 grams. I want to put this on top. I got so excited about writing that 58. Let me erase this really quick. Grams, of course, goes on top in this scenario. All right, so we have 58 grams of butane for every 1 mole of butane. So simply, we're just going to be able to cancel moles, and we're just going to multiply across. So we take 0.028 times 58, and we get 1.62. So that will be 1.62 grams of butane that's going to produce 2.46 grams of water. Now, what I want to do at this point is we've worked with butane already. We've worked with water. Now let's work with oxygen. Oxygen is written as O2 because it's diatomic within our balanced chemical equation. And we want to know how much oxygen was used up in moles. Well, we can take any known value we have now and use our mole ratio. But let me tell you the value that you most likely want to take is you most likely want to take the simplest value that has the less amount of math done by you. So for example, I'm going to use 0.14 moles because if I use this, I could, and it would be correct as well, but I had to do one more math. So if I made any mistakes here, then I have less of a chance of having the next ones correct. So I'm going to use 0.14 moles of water for my next problem. So if I have 0.14 moles of water and I want to know how much oxygen was used up, all I'm going to do, I'm already in moles, so I'm going to do a mole ratio because I'm going from one substance, water, to another substance, oxygen. So again, I look at my balanced equation and I have 10 moles of water according to my balanced equation for every 13 moles of oxygen, which is my coefficient in front of oxygen there in the balanced equation. When I go to calculate this, I am going to have 0.14 times 13 equals divided by 10. I'm going to get 0.182 moles of oxygen. So now I can say that I know how much butane I need, I know how much oxygen I need, I know how much water is going to be produced. And the final question is how much oxygen was used up in grams? So I'm just converting again. I'm taking my answer from letter D, and I have 0.182 moles of oxygen. And I'm simply going to convert that to grams. So moles of oxygen, again, it's O2, which is very important because that'll be important in our molar mass. So I have for every 1 mole of O2, I have 32 grams of O2 because remember there's 2 oxygens there. So I'm going to take 0.182 times 32 just to convert it to grams, and I get 5.8 grams of oxygen. So now I know how much oxygen was needed to produce that amount of water as well. All of this is proportional. You can use any part of the problem as long as you use the mole ratio to change from one substance to another. Let's look at number 2. We have an equation here with sodium hydroxide and sulfuric acid. So we have an acid-base equation that's going to produce water and then sodium sulfate. So what we want to know is how many grams of sodium sulfate will be formed if you start with 200 grams of sodium hydroxide. Here is our half. This is what's given to us right away. And you have an excess of sulfuric acid. Right now, you don't need to worry about this. All that this is telling you is, hey, that's nice. You have plenty. Okay, not needed. Nice, but not needed right now. It's just saying I have plenty of sulfuric acid. I don't need to worry about running out of sulfuric acid. What my need is grams of sodium sulfate. That's my need. So I start with what I have, which is 200 grams of sodium hydroxide. Here's the good part. If you forget how to name these things, you basically have a multiple choice in how you're going to name things from the chemical equation. But I'm going to start with grams of sodium hydroxide. And of course, I have to get to moles before I can do anything else. So I'm going to find the molar mass of sodium hydroxide. And we have 1 sodium, 1 oxygen, and 1 hydrogen, which totals 40 grams, is our molar mass of sodium hydroxide for every 1 mole of sodium hydroxide. So I've first converted to moles because that's basically whenever you have a number and you don't know what to do with it, just convert it to moles 9 times out of 10. Now I'm in moles of sodium hydroxide, and I want to get my needed sodium sulfate. So I look at my equation, and I have 2 moles of sodium hydroxide. This is my mole ratio right here. So for every 2 moles of sodium hydroxide, I'm going to need, I don't have anything written in front of my sodium sulfate, so it's just 1 mole. It's understood 1 mole. I'm going to need 1 mole of sodium sulfate. Now my moles of sodium hydroxide cancel, and I'm in moles of sodium sulfate if I would solve right now. But I need grams of sodium sulfate. So I'm going to have to go ahead and convert sodium sulfate to grams, just like we have been for a really long time. So we're going to say our molar mass. So our molar mass of sodium sulfate, we have 2 sodiums. Let's see, 2 sodiums plus a sulfur plus 4 oxygens, we're going to get 142 grams of sodium sulfate. Now, we cancel. Look at the units we're left with, grams of sodium sulfate. That's what we needed. So that's our signal to stop and calculate. So to calculate, we're going to take 200 times 142, so we multiply everything across the top, and then equals, divided by, multiply everything across the bottom, so 40 times 2, and we are going to get 355 grams. 355 grams of sodium sulfate. Now, what this says then, what this means, is when we start with 200 grams of sodium hydroxide and we run this acid-base reaction, we are going to end up with 355 grams of sodium sulfate. Let's take a look at number 3. Now we have lead 2 sulfate plus 4 moles of lithium nitrate yields 1 mole of lead 4 nitrate, sorry, the other one was lead 4, plus 2 moles of lithium sulfate. So what we want to know is how many grams of lithium nitrate will be needed to make 250 grams of lithium sulfate, assuming you have an adequate amount of lead 4 sulfate to do the reaction. Again, that's just saying, hey, you've got enough. You don't need to worry about having too much right now, okay? So 250 grams of lithium sulfate is what's given to us. That's the piece of information we have. And the grams of lithium nitrate is the piece of information that we need. So we're going to start with what we have, which is 250 grams of lithium sulfate. And we're first going to, you're right, convert to moles. So let's go ahead and convert to moles here. And we have 14 plus 32 plus 64. We get 110 grams is our molar mass of lithium sulfate for every 1 mole of lithium sulfate. Now, we are to the point where we want to change substances. So we're going to go from lithium sulfate to lithium nitrate because we want to compare the substances. And this is where we use our mole ratio. So we use the equation. Look up here at the problem, and we have 2 moles of lithium sulfate. So here's our mole ratio. For every 2 moles of lithium sulfate, we have 4 moles of lithium nitrate. The reason why I chose lithium nitrate again is that's our need, grams of lithium nitrate. If we cancel here, and if we'd solve our problem, we'd end up solving it in moles of lithium nitrate. But we want to continue because we need grams of lithium nitrate. So we're going to have 1 mole of lithium nitrate and find our molar mass of lithium nitrate. And it's going to be 7 plus 14 plus 48, 69 grams of lithium nitrate. So we can cancel moles of lithium nitrate. We're at grams of lithium nitrate. That was our need. So we can multiply now. So we have 250 times 4 times 69 equals, now we divide that by 110 times 2. And so we are going to get 313.6 grams of lithium nitrate. So what this is saying is if we have 250 grams of lithium sulfate produced, how much does it take of lithium nitrate to make it? And this will tell us I need 313.6 grams to make this. Stoichiometry is really, really important to figure out how much you can make or how much reactant that you need to make a certain amount of product. And it's actually one of the most important and most useful tools in analytical chemistry that you can do. All right, guys, I will talk to you again soon. You got this. Bye.